Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is lecture series on analog signal processing and we are doing 5th unit, the transconductance. Today's topic is elementary transconductance building blocks. As we have discussed in the previous lecture, the transconductance, what is transconductance, we have drawn some model for this one and we have seen its symbol and how it is represented. In transconductance, we have seen that the output current is equal to the transconductance into the input voltage. So it is a voltage controlled current source. The typical model we have drawn it for this one for the differential mode, where two inputs are given V1 and V2 and in output are negative and the positive terminals, same as in op-amp. So it can also be used for the operations. So it is called operational transconductance amplifier or OTA. Also we have discussed that this transconductance can be combined with capacitor to make different building blocks like gyrators, integrators, which are the basic building block for a filter to be designed. So most of the time we will use transconductance C, transconductance with capacitor. That's why it is called GMC filters, because we are using OTAs, that is operational transconductance amplifier, with capacitor. Now, in addition to this OTA and capacitor, we can have different resistors which can simulate the sufficient inaccuracy for the different range of the values. Another important building block is integrator that can be created using this transconductance C amplifier. So we can realize LC filters, LC ladders filters, which can be designed using the electronic inductors. So we can use transconductance for creating GMC filters as well as LC ladders, resistors, etc. So all can be created using electronic inductors. Now, how we can create a resistor? Let's suppose we have a transconductance with a single terminal. That means it has output current I0 and output, let's suppose, voltage is V0. So the equation for this this OTA will be IO is equal to GM into VI, which is a basic equation for the transconductance. Now, if we give this output VU to the input, so the input current will be equal to the output current, or we can say that I0 is equal to IN. From here, if we take the ratio of voltage and the input current, this will give the input ratio, input resistance. So now the ratio of from here VI by II will be equal to 1 by GM. This ratio is the resistance. So if we connect the output of this operational transconductance amplifier to the by giving feedback to the input, this circuit act as a resistor. So this circuit represents its resistor with resistance is equal to 1 by GM. Now one thing to be noted here, that this is a grounded resistor. because here we have Vi is with reference to the ground, and also the second part, that is the inverting input is also grounded. So when both the inputs are grounded, this we can take it as a grounded resistance. We have seen in the gyrator unit 4 that there is a difference between the grounded component and the floating component. So if we want to realize a floating component, floating resistance, let's suppose we have differential operational amplifier where we have two outputs, two differential outputs, and the two outputs are connected in such a way that they give the feedback to the input as well as to the output. Now if we pay attention, if we give this feedback loops, if we give this feedback loop, you can see there this I current will be equal to this I current, output current. So I can say that from here I can say that I is equal to I naught is equal to I, and the output current is Gm into the voltage difference, which is V1 minus V2. So from here again, if I say the ratio of the voltages and the current, that will give the resistance. So V1 minus V2 by I, that will give the resistance, which is again 1 by Gm. So this gives our floating resistance where the two terminals, where none of the terminal is grounded. So again the resistance is 1 by Gm for the floating resistor. Now if feedback is positive means if we are giving, here we are giving negative to the positive and positive to the negative, but if we give positive to the positive terminal in this way, such that positive terminal is given to the input of the positive resistance and negative is given to the negative of the input resistance, then we can say that Vi by Ii is equal to negative of R, which will be minus Gm. Now here you can see there in the Bruton's technique, we have created negative resistance, frequency dependent negative resistance. So it can also be used in such cases where we have some hypothetical or imaginary or we require impractical components. These components are like negative resistance that can be created using transconductance amplifier, which cannot be created in actual components. So second important concept of our filter design is integrator. Integrator is a fundamental component which is used for loading the transconductance by impedance. Now if we have, let's suppose, a transconductance amplifier, and let's suppose we have a some load Z is over here, then again by using the transconductance amplifier's equation, we can have output V2 is equal to Gm into the resistance into the voltages. From here, if we say V2 by Zs, that will be the currents. So I have converted current into the voltages. So voltage is equal to V2 is equal to Gm Zs into the difference of the two voltages. Two voltages are, let's suppose, V plus and V1 minus, depending upon the terminals. Now if this Zs is a capacitor, then I can draw the circuit in this way, where I have Zs is replaced by capacitor. Now for a single mode, small signal mode model, I will have the this capacitor C, which is in parallel with the output resistance, internal output resistance C0. The model's resistance C0 with a C. Now here it is to be noted that the differential output, this integrator is in the differential output, and so we can realize it in the both inverting and the non-inverting cases. This can be done by simply revising the voltages V minus and the V plus at the input. So we do not need different circuits or inverters for creating the different circuits, differential circuits. Also, inverter is idle, assuming transconductance is idle. We do not create non-idealities or non-linearities in the transconductance. So in reality, the voltage controlled current source is loaded with C node, as we have seen that C0 is in parallel with the C. Also there is a resistance R0, model resistance R0, which will both will be in the parallel with the C. So if we see the total effective impedances, that will be V2 by V plus. Here we have taken V2, as V2 will be the voltage over here. So this will be equal to Gm over S into C0 plus C plus G0, if G0 is the conductance of the resistance R0. So in real integrator, this integration capacitor is increased by value C0 plus C, which we are giving C only, but it has been increased by C plus C0. Also the R0, this G0 gives that the integrator that we have designed will be a lossy integrator, which will have some finite loss. This loss can be given by Gm by G0. So the 3 dB frequency, which will be equal to omega naught, is equal to G0 C plus C0. Also we have to check that the output capacitance CO value is very low, approximately 0.25 picofarad. So it should also be counted for the high frequencies, whereas we can neglect it for the low frequencies. So for this circuit, the circuit that we have designed for this circuit with the capacitor transconductance OTA-C circuit, we have this equation that we have driven. The output voltage by the input voltage is equal to Gm by S C plus C0 plus G0. If we calculate from here the output voltage, the voltage at the output V2 will be Gm into V1 R0 in parallel with C plus C0. So if I solve this inside the equation, it gives Gm S C plus G0. So this whole equation, this circuit that we have designed for the integrator. By this can be given into the currents by the transconductor. Then current is integrated on C to generate the voltage. So if we have voltage V2, the output voltage is V2, it will be equal to Gm upon SC into V1 if we do not consider C0 and V0. So this giving the integrator with constant Gm by C, integration of V1 with C. This is known as this circuit is known as the voltage mode, where we are not considering the currents, we are considering the voltages. So other type works as integrator the current I1 on C to generate a voltage which is then converted again into the current I2 into Gm by SC plus I1 by transconductance. By filtering, this type of integrator is termed as the current mode. Simply, if we take the voltages replaced by the same resistance, so I can represent it as V is equal to IR, R will be cancelled out, so I can write it as I2 is equal to Gm by SC I1. Now if this is in the terms of the current, it is known as a current mode. If it is in the terms, if we are calculating in the voltages, then it is termed as voltage mode. So there is a small difference between the voltage mode and the current mode transconductances integrator. Also, we can create this transconductance integrator by taking this capacitor here. Now if we see the transconductance in the different phase with the ratios of V2 by V1, this can be given as if we apply one resistance after this integrator to have the to remove the loading effect and to have the cascading equivalently, we can have V2 by V1, the total output by input, it will be minus of Gm by SC plus Gm2. And we have seen that 1 by Gm2 will be the resistance of this resistor. So the total, if we see the total resistance, total capacitor will be the with the output capacitor parallel to the input internal resistances and capacitor, then it can be given as V2 by V1 is equal to Gm plus to the two capacitances C0 for this as well as this stages, capacitor C plus Ci for the input resistance. We have Gm2 plus two internal external loads, which is external output resistances for this OTA as well as this OTA. So it is twice of C0 and twice of G0. Now we have created again integrator which is in the single-ended. So this is a single-ended integrator. Now as we have discussed that we have to design differential modes because of its many advantages. So now let's take a step ahead and move toward the differential input and the differential output for the OTAs. Let's suppose we have two single-ended integrators in such a that the positive and the negative signal paths are there. So one is we have drawn one circuit we have drawn is in this way, integrator cascaded with the resistance to give the total integrator. So integration do not change if we change the signs for the both input as well as the output. So if we invert these signs and we recreate this circuit can be drawn like this way, where we have changed the sign of the input voltage, output voltage and the terminals. Here we are giving the feedback from the positive terminal, here we are giving from the negative terminal. Now if we combine both the circuits, both these circuits, both terminals, the grounded terminals, then we have two C's at the negative, two C's at the positive side. One voltage is at the positive, one voltage is at the negative, and a resistance over here. So the input voltage is doubled by Vi plus minus into minus of Vi. So it gives twice of Vi. It gives twice of Vi. Similarly, current will be doubled. That is, I0 will be equal to twice of, I0 will be equal to 2 of I0. The capacitor should be doubled to leave so that the output do not changes. That's why we have taken here twice of the capacitance, so that the twice effect of current and the voltages do not affect the output. Now we can analyze the circuit, that whether this circuit can be acting as a true or actual integrator or not. Now if we see this integrator circuit that we have drawn, for this circuit, if we take the equation for the positive terminal and the negative terminal, this gives the nodal equation by this one. You can calculate the nodal equation for this terminal, and for the second path we can take the nodal analysis by this path, one path and the second path. We take the nodal analysis from the both equations, and from the two equations we can take the ratio of the output voltages and the input voltages. So it is V0 by V9, which comes to be minus of GM1 upon SC plus GM2. I have derived it. You can go through the steps using these equations. Now we can connect the differential mode capacitor and take their grounds off. So if we join these two capacitors by each other, right, then the whole equation will be in this way. This will not only save the area but also eliminate the extra capacitor requirement. So this will connected when it gives the C. Instead of 2C, it gives us C. So the circuit from this single input integrator, to make a differential output integrator, we have taken the mirror image. You can see the mirror image of this one by inverting the input and output connections. Then we have taken the twice of capacitance to eliminate the effect of twice of current and the twice of voltages. Then we have removed the capacitor by C by making the two grounded terminals connected to each other. So this will make our circuit for the differential mode integrator. So if we go with the steps, we can go the steps. Steps is like, first of all, we will take single-ended circuit. We will take the single-ended circuit. We will take the mirror image of this single-ended circuit. will change the polarities of the input and output so that it will not give any changes. Then we will double the value of all grounded capacitor, and any capacitor which is not grounded will be not changed. It will be unchanged. Lastly, discard any input that may be grounded, or the grounds may be merged for the correspondent active devices into fully differential ones. So we have combined the two grounds of the capacitors to make a fully differential output. So in this way we have created transconductance that we have seen in the last lecture. From there we have used that transconductance to create different different elements of the basic elements of the filters. We have seen the two basic elements today. One is the resistor. We have designed grounded resistor and the floating resistor. Then we have also designed a integrator. An integrator which will be using OTAs only, OTA and the capacitor. So OTA capacitor is also known as GMC filters. Then lastly, we have designed from the single input to the differential mode circuits. In the next lecture, we will see the other elementary designs and the filter, higher order filter designs. Thank you.